Welcome to part 2 of our lecture on strain sensing. In this lesson, we'll take a look at the basics of measuring strain. Let's begin by reviewing what we mean by stress and strain. In this case, I'm assuming I have a cylindrical bar of some material, and that bar has some diameter d and some length L. When I apply a force F to the bar expands to some final length L plus a delta L, and the bar contracts to a final diameter d minus a delta d. From here, I can define several important terms. The first one will be normal stress, that'll be sigma, and sigma will be equal to the force applied divided by the area in which it was applied to, so the area of the bar here. The axial strain, epsilon sub a, that'll be equal to the change in length divided by the length. So epsilon a will equal delta L over L. The transverse strain, epsilon sub t, will be equal to the change in diameter over the original diameter. So epsilon t will be equal to delta d over d. These two terms together, they'll define Poisson's ratio. So Poisson's ratio says that nu is equal to the transverse strain divided by the axial strain. And that ratio is always greater than 0 and less than 0.5. A few key points to note. One is that strain can be tensile or compressive, and a tensile strain is denoted as a positive, and a compressive strain is denoted as a negative, and that strain is dimensionless. It's also important to note that these strain measurements are often very small. We're looking at change in length over length or change in diameter over diameter. So strain is often expressed in terms of a microstrain. So in this case, we might have a strain with units of microstrain, which is still dimensionless. It's still meters per meters. But in this case, it's the original strain times 10 to the 6. So if I had a strain that was 10 to the minus 6 meter per meter, that would be 1 microstrain. Now, to measure strain, we're going to use resistive strain gauges. These strain gauges are fairly similar to the beam that we were just analyzing. It's effectively a chunk of something. And this chunk of material that has a length L and an area A, and if I were to connect that chunk of material to a voltage source and apply an input voltage, let's say V in, I'd be measuring a resistance. This resistance will be equal to rho, which is the resistivity of the material, times the length of the material all divided by the area of the material. So the resistance I measure will go up for a longer material, and it'll go down for a material with a larger area. Now the resistivity rho, that's given in units of ohms centimeters. So in this resistance that I'm measuring, I have a few geometric properties. These include the length and the area, along with an intrinsic material property, the resistivity rho. So when using resistive strain gauges to measure strain, we need to keep in mind these geometric properties. How is the length and the area of this sensor changing, as well as the material property? If it's a metal or some other material, what is the resistivity, and is that changing as the strain gauge changes, physically changes, stretches or contracts? Is that changing as well? Let's consider then a chunk of metal. And that metal has some resistance, which is a function of the resistivity, the material property, as well as the geometric properties, the length of the metal as well as its area. Then R here describes the nominal resistance of that chunk of metal. Now I'm going to strain that metal some delta L. So I'll now have some new resistance, and that'll be equal to the resistivity, and let's say that's constant, let's say that hasn't changed, times L plus a delta L, that change in length, divided by A minus a delta A. So that area of my chunk of metal has shrunk, has been reduced, so I divide through by A minus a delta A. And once again, I'm interested in determining what is this value of delta R, what's the change in resistance. So that'll be equal to R nu minus R. Now, if I have a delta R, a change in resistance, I could look at that if I could take the derivative of this equation here, but that's a bit cumbersome. So instead, I'm going to take the logarithmic derivative. In this case then, I'll find that the natural log of R, my resistance, is equal to the natural log of my resistivity plus the natural log of my length minus the natural log of the area. Now, we know from calculus that if I take the derivative of the natural log of x, the result is 1 over x dx. So if I apply this to my natural log equation, I end up with dr over r is equal to d rho over rho plus dl over L minus dA over A. So I've rewritten the equation here, and this dr over r, that's ultimately what I'm interested in. This d rho over rho term, that's going to describe any piezo resistivity I might have in my sensor. dl over L, that's my strain, so I'm going to write that as my axial strain. And then I have this dA over A term. And for this term, it's helpful to go back to that cylinder of material example. So the area is going to be this area, where A is equal to 1/4 times pi times the original diameter, d squared. So this dA over A term, that'll be equal to quantity 1/2 pi times d times dd, all divided by the quantity 1/4 pi d squared. This is going to result in 2 times the change in that diameter, dd, divided by d. And remember, this is effectively my transverse strain. So we could rewrite this term as minus nu times the axial strain. And thus that dA over A term can ultimately be described as minus 2 times nu times my axial strain. Now we can rewrite this dr over r equation as dr over r is equal to quantity 1 plus 2 times nu, that whole quantity, times the axial strain, plus my change in resistivity, d rho over rho. We can simplify this term a bit based on a piezo-resistive coefficient, we'll call that pi a, times the elastic modulus of the material times the strain that is applied. So this pi a term is dependent on the material that's being used and is ultimately describing a piezo-resistive coefficient. So if I wrap up all this information, I can now describe dr divided by r. That's going to be equal to the quantity 1 plus 2 times nu plus pi a times e, all times my strain. What's interesting about this result is that there's really 2 components here. There's a geometric factor, 1 plus 2 times nu, along with a piezo-resistive component as well. So depending on the type of strain gauge that you're using, the geometric or piezo-resistive factor, one may tend to dominate the change in resistance, one may tend to dominate more than the other. Let's rewrite that here for simplicity. dr over r, that's the output of my strain sensor, and I'm really interested in this dr term with respect to the nominal resistance r. I have my input, which in this case will be an axial strain, epsilon sub a, that'll be applied to my strain sensor. And then this term in the middle, we're going to call that the gauge factor, or GF for short. We can also define this gauge factor in terms of the change in resistance over the nominal resistance of delta R over R, divided by the change in length over the original length, so that'll be change in L over L. Using this gauge factor, I can then compute what my axial strain was. So my axial strain, that'll be based on some resistance that I'm measuring, some delta R, and that'll be equal to delta R divided by R, the nominal resistance, times 1 over the gauge factor. Let's take a look at a quick example. Let's consider that I have a metal foil strain gauge with a winding path of something like copper to give myself a reasonable resistance. So I have a nominal resistance, something like R naught is equal to 120 ohms, and since it's a metal strain gauge, we'll have a gauge factor of 2. And in this case, I'm applying a 1 microstrain strain to this strain gauge. I know that my axial strain is equal to 1 over the gauge factor times the quantity delta R over R. So delta R then will be equal to the gauge factor times R, the nominal resistance, times this axial strain. If I plug my numbers in here, that'll be equal to 2, gauge factor of 2, times 120 ohms, times 1 microstrain, so 10 to the minus 6. And thus my change in resistance, delta R, that'll be equal to 240 times 10 to the 6 ohms, which is also equal to 0.24 milliohms. So this is a pretty small change in resistance for this particular sensor. My new resistance then, that'll be R new is equal to R naught, the original resistance, plus my delta R. That's going to be equal to 120.00024 ohms. So just based on this simple example, you see the importance of our interface electronics to give us a acceptable sensitivity and ultimately amplification such that we can deal with such small changes in our signals, or in this case, such small change in resistance.